as the last speaker, we have Mario Collura from Trieste.
Thank you very much. Thank you to all the organizers. Since I'm the last speaker, I will try to be as fast as possible. And today I will talk about something which you already heard, because there was a talk by Lorenzo, the one by Guglielmo, and the one by Poetry. In any case, I will be just slightly fast in that part, which I don't want to reintroduce you on this magic and stabilizer formula. It's about magic, entanglement, and magic's product state, basically. The talk is extremely long in the sense that I will skip the majority of this. Let me just use this. Because
Maybe click on it.
Yeah. Let me first thank the people which are involved in these studies, at least in the one I will just present to you. Because actually in Trieste, the community of people start working on non-stabilizerness and manybody physics is exponentially growing. So now people are moving, they are no more in Trieste, there are a couple of them in Paris, other in... So they are moving, of course, but these at least are the one which have been involved in what I'm talking about. So let's start from the beginning. So quantum mechanics, which we know. Let's hope. Probably, I don't know. There are many things. So I learned about stabilizer formalism only 2 years ago, basically, because I come from manybody physics, not from information and quantum computing. No. So I know that in general, as a quantum state, it's a very weird and complicated object. And the most celebrated things in quantum mechanics in general, we learn at school that it's entanglement. No, so no, what makes special quantum states usually is the entanglement. But actually, 2 years ago, I learned that probably entanglement is not the only one. So sometimes, often, we need something more. And I hope, I will reintroduce you about this, but what I'm talking about is this magic, which is not the card game. Probably you don't know, but nevertheless. And this word in this talk will be referring to non-stabilizerness. The word has been introduced by Kitaev, because Kitaev can use this word. Otherwise, if you try to send a paper, this is important. So if you look, if you publish a paper in an APS review with magic in the title, they will complain. They will immediately ask you to remove that word, so to change to non-stabilizerness. But if you are Kitaev, you can do that. But let's keep a bit of what I'm talking about when I said, well, the complexity, magic, entanglement. I don't want to make people working in computer science angry on that. So I'm not saying that quantum computer, they will be useful probably. I hope. We know that in principle we can use that. This is a quantum computer, basically, you know? So you prepare a state, you do whatever evolution you want, unitary, and then you measure. We can use this to simulate quantum system. Well, why not? We can use this to try to solve our classical problem. Why not, as well? But of course, it depends how you design your computer. Maybe there are problems which are not so complicated to be solved. It's not so hard. So just for example, if you try to evolve a state with a genetic unitary evolution, you can produce a lot of entanglements. Now you follow this curve, which means you have to cross, which is called an entanglement barrier because of that. And to encode all these entanglements, basically you need a wave function which is exploding. You need an exponentially large number of coefficients, so it's hard to deal with this. But there are situations in which you can solve, for example, classical problem by engineering evolution operator which only require at the end in your wave function an area law amount of entanglement, which means at the end that you don't really need a quantum computer to do solve this problem. Now the point is,
what kind of situation?
that situation, it's for example, in some class of classical constrained optimization problem, in which your target state of your target Hamiltonian is still a classical state. Many classical situations happens. You may do evolutions in which you basically use MPS, you project your evolution in MPS manifold, and you get your results. And so basically you don't need all the entanglement to follow the real dynamics. That's the point. But it's not in general.
But do you have specific examples in mind?
What we did in this specific case, for example, what I was involved in this is for a perceptron Hamiltonian, which is a typical machine learning Hamiltonian, which you have, again, classical constrained problem. So you have some constraints and spin, and then you can solve classically. Yeah, you can find something here. But it's not the main, I mean, okay, so let me just tell you a couple of things that you already know. So entanglement, it's something which is related to the exponential number of coefficients you have in that wave function. Product state are classical states, we know. In between, we have something which we call matrix product state, at least in 1D, this representation. It's exponentially harder to compute expectation value in general. It's not exponentially hard, but it's polynomially complex if you use this wave function. Fine. Entanglement is something that people can measure. This is a way of measuring for manybody system. I mean, our manybody physics like very much. So to measure these entropies, this entanglement entropy, they are nice because they are somehow related also to this wave function ansatz representation of your system. So if you use an MPS, they basically are related to the bond dimension of this MPS. And then depending on if you are in 1D, 2D, you are ground state of gapped or no gapped Hamiltonian, you have many properties. It's something that is pretty much studied in our community. So, but the point here is that for a quantum computer to work, you basically need, what do you need? Okay, it's not so much reactive, this, just keep pushing. Anyway, so this is a quantum computer. So you have a circuit, you have a state, you apply your gates, whatever they are. And if you want to use an MPS, so you want to use an answer for your wave function, generally the bond dimension grow exponentially. This is the problem. So that's a volume law, this barrier, this is entanglement barrier. Then you can maybe change a bit point of view and say, okay, come on, why I have to evolve the state? Why do not can I evolve the operators? Because at the end we want to measure operators. But in general, this is not so you are just removing some complexity from one side and putting the other side. Except if you do some, you realize something. So first of all, let me introduce the Pauli group, which you have already seen probably in other talks. You have the groups of strings of Pauli matrices. Okay, so you just take n qubits, you have Pauli matrices, you take the tensor product of this, you generate a string, you have a sign in front, not really important, but you have a group. Any operator can be written in terms of this basis. Fine. Okay, and now you wonder whether if I take a unitary operator, this is what I was telling before, and you evolve a Pauli string, you get in general a linear combination of strings. Because the complexity cannot disappear. If it was complex to apply the operator on the state, it will be complex to apply the operator, the evolution operator into the operators. However, any unitary can be written in terms of these generators. These are local gates. Apart one of these gates, which is this C0 gate, which is acting on 2 qubits. Okay. Fine. If you restrict yourself into this subset, which are the generator of the Clifford group, then this is what happens, which is a huge simplification. Because basically you can have as many as you wish combination of operators here. Here you have just that one string is mapped to just a single string. We have to keep this in mind. This is important for. Okay, fine. These are just how is irrelevant. It's irrelevant, but this is not. Okay, what is relevant is that now we can identify a state by basically answering this question: how many Pauli strings stabilize that state? Which means how many Pauli strings are such that if I apply on the state is an eigenstate with eigenvalue 1. You pick up a state and you ask to yourself this. And you construct this, which is called the stabilizer group of a state. The stabilizers group is huge, or can be empty, whatever. But when it's such that the number of generators is equal to the system size, to the number of qubits, the state becomes a stabilizer. What it means that when you have a stabilizer state, instead of using an exponentially large number of complex numbers to characterize the state, you can use a polynomial large number of coefficients to characterize the state. So you just map an exponentially complex problem to a polynomial complex problem. As far as you have a stabilizer state, which means a state which was stabilizer group is generated by n, where n is the number of qubits, the number of qubits identifying your system. Okay, fine. And you can use a stabilizer formalism to evolve this matrix. Every time you use only Clifford operation on that. Because Clifford, they map generators of this stabilizer group, which are Pauli strings, into Pauli strings. And then this is what happened, basically. And then there is this Gottesman-Milne theorem that tells you exactly what I told you 1 minute ago, that if you prepare a state of qubits in a computational basis state, which are this 0 and 1, whatever, and you just apply Clifford gates, or you measure in the computational basis, this can be done with a polynomial number of classical operations. So in a classical computer, it can be done. Even the Bell state is a stabilizer state. So you have entanglement. So famous Bell state is just a stabilizer state. Okay. So complexity, if you wish, arise. And if we want a bit of quantum advantage, this happens. So we will have, once you introduce in the group of generators, there's T gates. Because when you have these T gates, then you have to deal with something which make your number of string of Pauli matrices explode when you try to apply this transformation, and everything becomes extremely complicated. And in fact, it's extremely important to try to quantify this, how many Pauli operation you need to prepare a state. And magic is exactly this. How far is a state to be a stabilizer? Then there are many different definitions to measure this, which basically the majority are based on minimization. It's extremely complicated to quantify this quantity. Now, let me tell you one thing, and this is the reason why I was saying that we were going fast. In principle, I could discuss with you about how to quantify magic or how to enhance classical simulations. I may ask you what you are interested more, but I don't want any reply because I will go straight on the second point. So I will skip the first part. If you are interested, you may ask in later. So I will skip, which means you just look at slides which are irrelevant if I'm able to skip. But basically, by skipping, I want to tell you just a couple of things, that this magic can be measured by using this stabilizer Reni entropies, which have been introduced by Lorenzo Leone, which should be in the audience. And when you want to measure this quantity in a wave function, which is special, is an MPS wave function, this can be done efficiently. This is you can even extract a stabilizer group, so the number of generators associated to a specific MPS, but it's not the, I don't want to spend time on that. I want to really go on the last part, which is longer than this. So let me just go there. It's fine, it's fine. Okay. This is, so 10 minutes, fine. Clifford operations are important because in some way, when you use Cliffords to the operators, they don't, they keep the complexity of the operators. Imagine to have an operator which is a linear combination of Pauli strings up to a given number. If you do a Heisenberg evolution of this operator, this number can grow exponentially, so it can be whatever. But if you do Clifford evolution of these operators, this number remain unchanged. It's bounded. But then the idea is, let's suppose that you have an MPS. Okay, so just an MPS that describe your state, which in general has a bond dimension. And you want to evolve, no? You want to just jump from here to there. Okay, and since U1 can be complicated as you wish, in general, so this is an auto-equilibrium situation, this bond dimension is growing, is getting larger and larger. But then you can say, okay, come on, why could we use any Clifford transformation that reduce the amount of the entanglement in your MPS wave function and that transform U1 in something else? And then we follow this other evolution, which require less classical resources. So probably I can finish the talk here because this is the main message. Because the answer is yes, but it's of course model dependent. It really depends on what we are trying to solve. But now let's try. So one situation is quite simple. Is when you, for example, have this quantum circuit. So you prepare your system in this 0, 0, 0 state. You want to apply whatever Clifford operation. Then you have, for example, a local rotation, whatever it is. Then you have another Clifford operation, then rotation, and so on. And then you want to measure a string of Pauli matrices. In general, when you apply C1 to the state, this can have a volume law entanglement immediately, because this can be as deep as you wish. However, using this stabilizer formalism, due to the fact that this rotation is just the sum of two Pauli strings, and since Clifford can map Pauli string to Pauli strings, in particular the identity is mapped to the identity because it's just the identity, you can rewrite this operator as an NPO of bond dimension 2. And then you can transform this network to this one, this one, this one, which is a two-dimensional tensor networks, which all this line, all the black line you see have bond dimension 2, are just qubits. And then you can contract this in whatever direction you want, which is more efficient. Even if you contract in the usual direction, you get some advantage. I mean, this is the operation you get there. You get some advantage. Let me just show you in some specific scenario. So this is the simplest scenario. So you have Clifford, which are made by this checkerboard structure up to a given depth T. Then you have a T gate, and then you repeat, and this is Clifford at random. So you just use random Clifford operation. And if you measure the entanglement of the states that you can get by just applying the entire Clifford on the state, then the T gate and the Clifford and so on, you get this curve. However, if you use the method I was just mentioning before, so you are commute and try to get rid of some Clifford operation, which can be basically applied in the observable, you have much less entanglement in your effective states. And this is in many, I mean, it's pretty independent on the deepness of C, because no matter how deep is C, you map a Clifford, it's a Pauli string into Pauli strings. So it's just that if this is bigger, the usual entanglement is grow much faster at the beginning. When you don't use this algorithm. Yeah, these are just a different simulation for different bond dimension, main realization of your Clifford circuit, because these are random Clifford. Sorry? This is the depth of this Clifford. This is another scenario in which usual MPS algorithm cannot be used at all, because you can apply this we want to mimic like a sort of Floquet dynamics with Clifford. And we did this by saying, okay, why not to apply a random unitary Clifford which is U1 symmetric, and then apply a rotation as usual when we use this Floquet, not by pi alpha, but slightly different from pi alpha, in such a way that if epsilon is 0, you just have this time crystal, this up and down spin pointing first up and down and so on and so forth. If you have epsilon, your order parameter is decaying, but this is an arbitrary U1 symmetric Clifford unitary over n qubits, which cannot even apply to that wave function in an MPS formalism. Wow. And basically, with this method, you can at least get some results. Now, let me just mention one thing. This P-doped circuit that we were mentioning before can be recasted, just to be in connection with something which has been discussed here about measurement, can be recasted into projective measurement and Clifford circuit using a formalism which map a T-gate into this operation, which is a projective operation on some ancillary gates, ancillary qubits prepared in these T states. And in this paper, a classical algorithm has been basically proposed to solve this Clifford and projective measurement dynamics when the initial state is not a stabilizer state. I don't go into the details because we have just 2 minutes, and let me just do a step forward and say, okay, but the more general setup will be to try to evolve a manybody state by following an Hamiltonian dynamics. So Hamiltonian dynamics means that I have a unitary operator that is e to the power of e minus eh dt, for example, after totalizing. And by using MPS, usually the bond dimension explodes, we know, because it's growing linear exponentially in time. Is there any way to improve this evolution in a classical computer? Well, we can use this basically ansatz, which has been introduced by also by Jacopo and Guglielmo and Tobias, which has this Clifford enhanced MPS. Now, the problem is to optimize this Clifford circuit to apply to your MPS in order to reduce the entanglement. You cannot randomly take a Clifford from the huge group of unitaries for n qubits. So if you give to the Clifford this structure, which is the one I was showing before, so just a checkerboard structure up to a given depth, you can hope to optimize locally these unitary gates by just reducing the entanglement entropy in an usual DMRG sweep. So usually, let's suppose you have a state, you apply this gate, you compute the new singular value, and you try to find the best gate that reduces the entanglement entropy of your state. This can be done just by searching in this group.
Sorry, you do this search locally.
Locally.
So it's not the circuit which minimizes the entanglement. You do it gate by
Yes,
gate.
yeah, it's not. Otherwise, you have to do global search. But
In principle, that's what you would like to do.
okay, but
You do this minimization gate
by doing like a sweep, like in DMRG, basically. Yes.
Can you check how far is it from the global minimization, at least for very small cases?
We didn't. But what you get, it's that the Clifford then can do not increase the operatorial representation, the MPO form of your Hamiltonian, the complexity, because are Clifford. So basically you can transform back this. So an MPO of your Hamiltonian remain like that. And then you can use a TDVP scheme as usual, no problem. And let me just give you an example. This is a very simple example. Then we benchmark another model, but this is the XX model. We know the exact solution at least, so we can compare. And here, I think the more interesting curve is, okay, I can comment to that, but the full line is the exact evolution, because these are free fermions, so we know. The green one is the TDVP solution at the given resources, which has been fixed by the TDVP for that system by running a usual TDVP. And the dotted are the disentangled solution. So you reduce the entanglement and you allow your MPS with the same bond dimension to be more accurate in describing the exact dynamics, basically. And the accuracy is measured here by just comparing the distance with respect, the integrated distance with respect to the exact results, which scale with the bond dimension in some way.
What is K?
K is, this is something that I didn't mention. Anyway, you can call in your algorithm the disentangler routine in any moment of your evolution. So K1 is when you basically call this disentangling routine at every trotter step. K10 is at every 10 trotter step. It's up to you. You can choose. In this case, K10 for this specific scenario is not working very well.
It seems worse than not doing it at all.
Yes.
Okay.
Because in a way, the disentangler, if the state gets entangled too much, probably in this local minimization is not able to restore properly, to remove properly the entanglement, and it's too much. I mean, it's true that your operator is not getting. It's true that in the operator representation of the Hamiltonian, the number of Pauli strings remain unbounded, but it's not true that the Pauli strings are changing and then they get more broad and then everything becomes slightly more complicated. But well, okay. So let me just conclude with this picture because the take-home message. The take-home message is the following. It's written there, basically. So we try to use Clifford, the stabilizer formalism, and matrix product state together to reducing complexity of, in principle, hard complicated problem, which is a quantum many-body evolution. This can be done up to a point, because the point in which you cannot anymore separate magic and entanglement is exactly the point at which your disentangler is not working anymore, basically. And from a pictorial point of view, this is what's happening, basically. So you are trying to solve a very complicated evolution, putting all the Clifford operation in one side, all the magic operation in the other side, but there is a point in which the state you are trying to reproduce need some quantumness. Because this state here will be classical, basically, due to the Clifford formalism and the product states that you have on the right. So there are points in which you have some quantumness, basically. And thank you for your attention.
Thanks for the talk. This is very interesting. Have you thought to generalize these two instead of taking Clifford and T-gates to pre-fermionic Gaussian unitaries and for quartic interactions, stuff like that?
Yes, yes. So actually, we know, we perfectly know, and thank you for your question, because this is allow me to say something. Of course, all this depends on the free resources. So what you are able to do in a quantum computer and what you are not able. So here I am assuming you are able, due to this stabilizer formalism, to do Clifford operation, and then the complicated part of it is a T-gate. For example, non-interacting fermions and the interactions, what we are able to do is to treat Gaussian states, and then the interaction need to be treated in a different way. Actually, we are thinking about that, but there is some work by Studd and Miles, in which they basically did a very similar things for MPS Gaussian disentangler. So you have basically an MPS, which is in a fermionic language written, and then you evolve, but you try to disentangle this MPS by diagonalizing the two-point correlation function. Because if you know that the best representation that you can use for an MPS, fermionic MPS, if it's Gaussian, is when your two-point correlation function is diagonal. That is, can be a global phase, is a global change of basis, but it's the best global change of basis that you can use. This is not true anymore for an interacting model, but can be the best. And they did something. They exactly address the question you were asking.
Thanks.
So coming back about this optimization and finding this optimal Clifford. Yeah. If I give you a random Clifford,
okay,
state generated by random Clifford, and now you say, okay, I want to bring it back to some product state. Can you use this? Will it work?
This is, I think we checked it. It works. I think it works.
So you find it. You
yes.
go back.
Yes. So you see. So okay. Yes. Yes. In that case, yes.
So by local optimization, you can really invert a generic cliff.
Actually, I can tell you even more. If you prepare a T-doped state where you just prepare your state as a computational basis state, so the zero reference state, and then you apply an arbitrary deep Clifford, then a T-gate, an arbitrary T-gate, then an arbitrary, so exactly the circuit I was mentioning before, and you try to disentangle that one, you are able to perfectly disentangle that circuit as far as the number of magic gates that you are applying to your state, so that are in the circuit, are equal to the number of qubits. Up to that point, you are able to factorize the state. So, I mean, basically, able to get back to the picture I was mentioning at the end. So you just have, yeah, you just have this. I don't know what happens, but it's not important. Ah, okay. Yes, sorry, yes.
All right, I think we are.
Yeah.
We used time well.
Yes, I think so.
Let's thank Mario again.
I think we have to thank the organizer now for this very nice
and Francesca.
And Francesca, yes.
The Institut Pascal for having.
So thank you very much.